Welcome all. So, today we will be looking into the multi-degree of freedom analysis of the multi-degree of freedom system. We will start with the basics that we know. We will take a real life system. We will quickly go into the details about the single degree of freedom approximations, the 2 degree of freedom approximations, and we will use the same analogy to formulate our problems in the multi-degree of freedom systems. So, let us start the course. So, first we will start with the static force displacement relationship. Okay. So, we have seen a, let us take a simple example. Okay. Let us take a beam. Okay. Okay. So, in a beam, in order to describe accurately the position of the system at any given instant of time, we have to know the information possessed by the all the degrees of freedom. Okay. So, there are in principle infinite degrees of freedom. Okay. Now, in order to analyze the system, what we started is that the response of the at any given instant and for any given degree of freedom, okay, or at any place, okay, will be a summation of all the modes. Okay. It means that this system is going to vibrate in all the modes. Okay. So, these are the different modes of vibration of the system and so on and so forth. So, my total response, okay, at any point, okay, if this is the chosen degree of freedom, okay, then this response, okay, y at chosen degree of freedom will be a summation of all the mode shapes, okay, and it will be multiplied by a factor, okay, okay, that will give me the amplitude. Okay. But the total response will always be a summation or a contribution from all the modes. Okay. So, that is how we started our analysis procedure. Okay. And when we started our analysis procedure, if we are interested in the maximum deflection, okay, and if the system is going to predominantly, if the applied load on this particular system, okay, if this is in this uniform phase, okay, we argued that the first mode, okay, will contribute to a greater extent. Okay. Let us say that if this mode is contributing 95 to 96%, okay, then we say that I can analyze this system with 95 to 96% accuracy, but with much ease. Okay. So, at that point of time what we did was we ignored the contribution from the other modes, okay, and we just substituted our system as a single degree of freedom system. So, we choose the point where the maximum deflection is going to occur, that is we choose at y at center, the degree of freedom was chosen at center, and we took the one mode only, we took the first mode. Okay. So, though the accuracy is low, but the ease of doing the calculation is fast. Okay. So, this was the single degree of freedom system analysis. Okay. After that we increase the complexity of the system. Okay. We said that we are interested in calculating the degree of freedom, let us say at 2 different points. Okay. Then we have to choose 2 degrees of freedom, and after that we are also taking the help of 2 modes. Okay. So, the first mode and the second mode. Okay. So, this was our analysis for the 2 degree of freedom. So, for single degree of freedom system, y is a combination of q1 and phi1, and for a 2 degree of freedom system, y at any given instance is a summation of the contribution from the first mode and contribution from the second mode. Now, we are extending this analogy and we are trying to calculate y for a multiple degree of freedom system. Okay. So, here x1, x2, x3 up till xn, okay, are defined as the coordinates used to specify the deflection configuration of the system in a dynamic analysis. Okay. Let us say we are taking this for a case of a simple beam. So, here we are describing the deflection of this beam. Okay. So, we are discretizing the continuous points in terms of x1, x2 up till xn. Okay. So, this choice where we are taking more than 2 degrees of freedom, that is we are taking multiple degrees of freedom. So, this is called a multiple degree of freedom analysis. Okay. Okay. So, we are assuming that at point of definition of this coordinates, okay, the system is acted upon by a set of concentrated forces. Okay. So, this might happen, this might not happen. Okay. So, let us say that this is our total uniformly distributed load. Okay. So, what we are saying that at the chosen degree of freedom, okay, this force is acted in a concentrated sense. Okay. So, we are discretizing the degrees of freedom also from a continuous system, we are discretizing into a multiple degree of freedom system, and also we are discretizing the contribution from the individual forces. Okay. So, here each one will see its own different forces. Okay. So, this forces produces the displacement x1 x2 in the direction of forces. Okay. Or if you look into our other analogy, we can say that instead of 2 masses, now we have infinite number of masses. Okay. So, this was mass m1, mass m2, mass m3, mass m4 till mass mn. Okay. So, then this was the chosen degree of freedom x1, x2, x3, x4 till xn. So, at each chosen degree of freedom, okay, our forces are acting F1, F2, F3, F4 till Fn. Okay. And this we can represent using our spring system, okay, spring and dashpot system. Okay. This is the spring and dashpot system. Okay. There is a break because the other masses are there. Okay. Okay. So, in the starting we started with a single degree of freedom system, we looked into the 2 degree of freedom system, and now we are extending the same analogy to a multiple degree of freedom system. Okay. So, this is the beam approximation and this is the concentrated mass approximation. Okay. So, now for this system, okay, if we ignore the dynamic nature of the system, okay, we are considering this thing as a static system. So, if we try to write the response of the system, okay, in a static sense, okay, we can write that F1 is due to the summation of all the degrees of freedom. Okay. F2 also follows the same path. Okay. So, we can write in terms of force balance also, or we can use the relationship between the displacement also. Okay. So, this we can do. Okay. So, we are first trying our hands with the static approximation of this multiple degree of freedom system. Okay. So, the quantities D are known as the flexibility coefficients. Okay. K quantity we are very conversant with it. So, we call this quantity as the stiffness quantities. So, D quantity, a similar quantity, it is known as the flexibility coefficients. Okay. So, these are the stiffness coefficients, these are the flexibility coefficients. Okay. So, D are the flexibility coefficients and K we very well know, these are called the stiffness coefficients. Okay. So, now we will try to establish the meaning of this particular coefficient. Okay. We see that each of the coefficient, okay, be it stiffness coefficient or be it the deflection coefficient, this is always represented by a 2-letter subscript. Okay. So, we will try to see what is the meaning of this subscript. Okay. So, to establish the meaning of a particular coefficient, consider the equation that contains that coefficient by making the displacement of the term containing the coefficient equal to unity and all other displacements equals to 0. Okay. Then we will interpret the meaning of the term on the left. For example, to determine the meaning of D21, okay, let us say we are trying to see what is D21. Okay. So, we are trying to see what is the meaning of term D21. Okay. So, we will do one by one. So, we will try to see what does D21 means. We considered the second of the equation in 1 and take F1 as 1, okay, and F2 other F's are 0. Okay. Okay. So, D21, okay. So, we considered this term only, okay, and all other f we are considering this thing as 0, okay, because this one is 1 and we have switched off all the other f, okay. So, everything is gone, okay. So, it means that d21 is nothing but the displacement at 2 produced by a force of unit magnitude at 1 and no other forces is acting anywhere, okay. So, this is the flexibility coefficient produced by a unit force, okay, which has a at 1 and no force is acting anywhere, okay. Okay. Similarly, in order to determine the value of meaning of K21, okay, we will look into the term K21, we will look into this term K21, okay, K21, okay. So, we consider the second equation in 2 and take x1 equals to 1, okay, and all other x are 0, okay. So, x1 is 1 and all other x are 0, okay. So, it means that K21 is nothing but it is force at 2 produced by a displacement of unit magnitude at 1 and no displacement is acting anywhere, okay. So, this K21 becomes the magnitude of the force produced at 2, okay, and this is caused by a displacement of unit magnitude at 1 and no other displacement is acting anywhere, okay. So, similarly, in matrix notation we denote the flexibility matrix and the stiffness matrix in this sense, okay. So, remember, for a multiple degree of freedom system, now we are trying to do a static approximations because we want to evaluate the stiffness or the flexibility matrix, okay, where K and D are square matrices of the stiffness coefficients and the flexibility coefficients respectively, and F and X are the column matrices of the forces at the nodes of the associated displacements, okay. The matrix D is known as the flexibility matrix of the system and K is known as the stiffness matrix of the system, okay. So, substituting 3 and 4, okay, okay. So, we are substituting this thing. So, we conclude that if we multiply the stiffness matrix with the flexibility matrix, we will get the identity matrix, okay. So, what we have simply done is that this was the force matrix, force was stiffness matrix times the displacement, okay. This thing is, this matrix is again given by, okay. So, we are getting force was back, it means that this term is the identity matrix, okay. So, this is a identity matrix. So, it means that K and D should be the inverse of one another, okay. So, from Maxwell law of reciprocity, it follows that Dij equals to Dji, okay, and hence the flexibility matrix is symmetric, okay. Similarly, from Beatty's work principle, it follows that Kij equals to Kji, okay, indicating that K is also symmetric, okay. So, if we take these two principles, okay, Maxwell's and Beatty's principle, we see that the using the law of reciprocity, okay, both the matrices, the stiffness matrices as well as the flexibility matrices, both are symmetric, okay. So, evaluation of K and D, okay, how to calculate K and D, okay. So, what we normally do, okay, we will see how to calculate the value of K and D, okay. So, in order to calculate the first value of D, okay, what we do is that we apply this amount of, so this is given by so here for calculating D, okay, at joint 1, okay, at degree of freedom 1, we apply the force, okay, and we calculate the flexibility out here, okay. Or if we are talking in terms of stiffness, here we apply a unit deformation, okay, and we calculate the forces out here, okay. So, the force required, okay, to make this thing go 1 unit, okay, applied at joint 1 1 is the stiffness requirement of all the points. Okay. Similarly, for the second point we apply a unit deformation, okay, and the force required, okay, the force required to carry to get this system in this particular shape is the stiffness matrix. Okay. Similarly, we apply a unit force. So, the displacement quantity becomes my flexible quantity. Okay. Similarly, we keep on applying the amount of different displacements, okay, and we calculate the equivalent flexibility. Okay. So, this becomes the first column of the flexibility matrix, this becomes the second column of the flexibility matrix. Similarly, first column of the stiffness matrix, second column of the stiffness matrix. Okay. We are talking about this terms. Okay. So, here, okay. So, what we have done here is that here we have applied the deformation at x1, okay, or we have applied the force at f1, okay, and we have calculated the values of the different k's. Okay. So, that becomes the value of this forces. Okay. So, we have given a unit deformation. Okay. So, here again if you look here, so what we did was we took the system, okay, we took our system having different degrees of freedom, and at x1 we gave a unit deformation. Okay. So, at x1 a unit deformation was given. Okay. So, in order to have this shape we calculate the amount of forces required. Okay. So, that forcing value is nothing but the value of my K11, K21, Kn1 and so on and so forth. Similarly, to calculate the flexibility matrix, what we did was similarly at the degree of freedom we gave a value of unit forcing function. Okay. So, the amount of displacement that it occurred is the value of my flexibility matrix. So, if you looked into the column wise, we can calculate all the forces. Okay. Okay. So, that is why it is written the second column of stiffness matrix or second column of the flexibility matrix. Okay. So, we will try to do this example. So, in this example we have 3 degrees of freedom x1, x2, x3 and there are stiffness K1, K2 and K3. Okay. So, the flexibility matrix. Okay. So, if you looked into the flexibility matrix, okay. So, here we are giving the unit force, okay, and the corresponding deflection we are measuring. Okay. So, that becomes my column matrix. Second way, similarly at x2 we are giving, okay, measuring it. Okay. Similarly at x3 we are giving it and we are measuring it. Okay. So, this formulates our stiffness matrices. Okay. Okay. So, similarly the element of the stiffness matrix we obtain by giving a unit displacement out here. So, we give a unit displacement at the degree of freedom x1. Okay. So, the amount of force required to cause this displacement becomes my value of my stiffness. Okay. So, this is given by this equation. Okay. So, again here we give a unit displacement here and the amount to cause. Okay. So, the amount of forces, okay, that happens is the amount of force required to cause this shape, to cause this unit displacement becomes my value of my stiffness. Okay. And similarly here we give a unit displacement at K3 and the amount of forces required to cause this system, okay, again becomes my column matrix. Okay. So, this is we arrange column matrix by giving unit displacements, okay, at the chosen degree of freedom. Okay. And these 3 degrees of freedom we rearrange them, okay, and if we measure the forces associated with it to cause this displaced shape, to cause this displaced shape, and to cause this displaced shape, it becomes the stiffness matrix. Okay. So, this is the simplest way we can calculate our stiffness matrix. Okay. What we can also do is that we can go back and see the analogy from a single degree of freedom system. In the single degree of freedom system, if you remember, if we are looking into a beam, okay, and if we are just trying to calculate, if we are measuring this thing as the degree of freedom at y at center, okay, and if we want to make this system, okay, if you want to make this system, okay, so what will be the value of k? Okay. So, at the chosen degree of freedom, okay, at the chosen y, we give 1 unit displacement, okay, we give y equals to 1 and we calculate the amount of force required to give a unit displacement. Okay. So, as per the deflection equation, the value of y equals to let us say this is a loading P. So, P L cube over 48 EI. Okay. So, 48 EI over L cube times y becomes P. So, if I am giving a unit displacement out here, if y equals to 1, okay, what is the amount of force required? Okay, it will be equal to this number. Okay. So, the value of the stiffness, okay, if y equals to 1, okay, if y equals to 1, what is the value of the force required? The value of the force required becomes 48 EI over L cube. The value of P becomes 48 EI over L cube. Okay, and this P is nothing but my stiffness in the system. Okay. So, the amount of stiffness is defined as the amount of force required to cause a unit displacement. Okay. So, similarly, same thing we are doing out here. Okay. So, here in order to calculate the stiffness matrix, we are trying to give a unit displacement as at the chosen degrees of freedom. Okay. So, we have defined the degrees of freedom x1, x2 and x3. Okay. So, x1, x2 and x3. So, this whole column will corresponds to a unit deflection at x1. So, we are giving a unit deflection at x1 and we are calculating the force required to cause this unit deflection. Okay. So, these are the values of the forces at the corresponding 3 degrees of freedom. Similarly, for the second case, we are giving a unit displacement at x2, okay, and we are trying to calculate the forces required to cause this deflected shape. Similarly, for the third case, we are giving a unit displacement x3 equals to 1 and we are trying to calculate the required forces. Okay. So, this is how we calculate the stiffness matrix. Okay. Same analogy we have used for the single degree of freedom system. In the single degree of freedom system, if we want this deflected shape and if we want this stiffness, okay, we will write the value of the deflection y equals to PLQ over 48 EI. Okay. So, y equals to 1, it means that we are giving a unit displacement and the amount of force required 48 EI over L cube is the value of the amount of force required becomes the value of my stiffness, okay, in order to cause this particular shape. So, similarly, we are solving for this part. Okay. So, in this particular way, we can derive the stiffness equation for as many number of degrees of freedom are given. Okay. So, let us do the same thing for a cantilever. Okay. So, there is a cantilever. Okay. So, what we can do is that we can go by the deflection approach also. So, what we are trying to do is that we are trying to calculate the flexibility matrix. Okay. So, here we are having 3 nodes, okay, node 1, node 2, node 3. Okay. So, in the earlier case we saw the same example using the stiffness approach. Now, we will see the same example using the flexibility approach. So, in the stiffness approach we were giving unit displacement, here we are trying to give the unit forces, okay, and we are trying to calculate the deflection that is occurring in the system. Okay. So, depending upon the choice of our degrees of freedom, okay, depending upon the choice of our degrees of freedom x1, x2 and x3. Okay. So, we will try to give the unit forces, okay, will apply a unit force, will apply a unit force, will apply a unit force, okay, and we will calculate the deflection caused by this unit forces, okay. So, let us say x1, x2 and x3. So, first of all we will give the unit force F1 equals to 1 out here, we will calculate the value of the deflections, then we will give unit force at this point, unit force F2 equals to 1, and in the third point we will give F3 equals to 1, okay, and we will calculate the, or we will record the deflections, okay. So, this will become the individual columns, okay. So, this way we can assemble our stiffness matrix, okay, sorry, this way we can assemble our flexibility matrix, okay. So, in the first case what we did was we gave unit displacement, we calculate the amount of force required in order to cause that particular displacement shape, and we recorded those particular force values, okay. So, these forcing values are nothing but the stiffness coefficients, okay, in order to cause the unit deflection, okay. In the second case we took out a cantilever beam and we applied the unit forces, okay, at the 3 degrees of freedom, and we calculated the deflections, okay. So, these deflections are nothing but my flexibility coefficients, okay. So, in this way interchangeably we can calculate the stiffness coefficients and we can calculate the flexibility coefficients, and the flexibility coefficients and the stiffness coefficients are inverse of each other, okay. They are symmetric also using Maxwell's and Bette's law, and they are inverse of each another, okay, because they come from the same equation F equals to kx, okay, and interchangeably you can write x equals to d of f, okay. So, from the same equation they are just the rearrangement, so they are inverse of each another, okay. So, today what we did was we started with the multiple degree of freedom system and we tried to calculate the first part of the system, that is the stiffness coefficients or the flexibility coefficients required to calculate the stiffness matrix or the flexibility matrix of the system. So, in order to do that we used our static principle. So, as we have earlier defined, the stiffness is nothing but the amount of force required to cause a unit displacement. We used the same principle and we saw that example where we took a multiple degree of freedom system. We kept on applying the unit displacement at the different degrees of freedom and we calculated the associated forces. Those associated forces are nothing but the stiffness of the system. Same analogy we applied and we took a cantilever example, and in the cantilever example we took the multiple degrees of freedom system. In that particular multiple degrees of freedom systems we kept on applying the unit forces one by one and we calculated the respective deflections caused by the unit forces, and those deflections are nothing but my flexibility coefficients. So, in this process we can make our flexibility coefficients as well as the stiffness coefficients, and they are symmetric as well as they are inverse of one another. So, if we have one of them we can easily calculate the other. So, this way we have established the how we can calculate the stiffness or the flexibility coefficients using our static rules, and next time onwards we will move into the calculation for the mass matrix. I will stop here. Please practice these things. Thank you.